So we looked at last day at the lawnmower question. I like the lawnmower question. I like the lawnmower question. There's a bunch in your homework for this lesson. Static equilibrium, not on your test yet. We will do a whole unit on it towards the end of the year. But the reason I like it is if you're in static equilibrium, if you're not moving, what's your acceleration? 0, which means what's your net force? 0, which means first of all, if it's an equation like the one I just went over with Jake, that makes the equation way nicer because when it's winner minus loser equals 0, especially the one that you and I were doing, because it normally would have been m1 plus m2 times a. No, if a is 0, then a times m1 plus m2, still 0. Made the equation much nicer. Or if you have vectors, they add to 0. What do I mean by they add to 0? You end up with a triangle that goes nowhere. So I said, pause here. Let's go rock climbing. And I added a part D if you want to add a part D. The part D says, find the friction force between the climber's shoes and the cliff. So here's a climber, rock climber. It says in the diagram below, assume the mountain climber's feet are tending to slip down so that friction is up. The climber is at rest. You know what, Colin, I would underline the phrase at rest. That means we are in static equilibrium. That means the sum of the forces is going to be 0 because we're not accelerating. A says, write force equations relating the force components. We're actually going to do that in our free body diagram along the way and just take care of it. Really what I'm interested in is we're going to find part B, the tension, part C, the normal force. Apparently there is a normal force. And then part D, the friction force between the climber's shoes and the cliff. So free body diagram. Here, I'm actually going to draw a free body diagram. I'm going to say to myself, self, here is the climber. What are the forces acting on him? Get the obvious one. What else? Definitely a normal force kicking out from the cliff. There's a rope. Tension, and on the climber's torso, on his center of mass, that's it. Now you're going to, where's friction? Patience, patience. Those are the 3 forces acting on the climber. Now, what friction is doing is, in this position, if this was ice right here, what would happen to his shoes? And he'd start tumbling, spinning, not accelerating up or down, just spinning in place. So what friction is doing is keeping him from spinning, but it's not actually holding him up. It's not actually counteracting gravity at all. So we're going to come back to friction, but I'm not going to put it in my free body diagram. How many forces have I drawn? Is there more than one force at angles? Yeah, I got one slanty and one horizontal and one vertical. To solve this, I'm going to add these together. How am I going to add these together? I'm going to draw them, tip to tail. I'm going to draw the easiest one first, gravity. I always draw the toughest force next, tension, because it's at an angle. Would I want to stop right there? No. Tice says no. Tice is right. Would I want to go this far? No. In fact, I know when to stop because I know the direction of the third force, dead horizontal. So I'm going to go draw, 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 stop right there. There's the normal force. And did I come back to where I started from? That is a picture of 0. That's a net force of 0. Where does this 8 degrees go? Well, I notice between tension and a vertical line, it's 8 degrees. I think between tension and a vertical line, it's 8 degrees. Part A said, write force equations. They gave me the mass of the climber. Well, they gave me the mg of the climber. This is mg because they gave it to me in newtons. Oh, what did we call that when they give you, instead of mass, in newtons? Begins with the letter W and rhymes with the number 8. Okay, we gave you the weight. So I can just say, by the way, this is 650. I don't need to times it by 9.8 or anything. So since this is what I know, I'll use this to write my equations. Normal force, opposite, adjacent, or hypotenuse. Tension. The weight, mg. Adjacent. That's the one that I know. Can you write me a trig equation for tension and the weight? Cosine of the angle equals mg over tension. How would I get the tension by itself? It's on the bottom of a fraction, Jake. You know what? What I would do, I would say, hey, this is 1 fraction equals 1 fraction. Stuff moves diagonally. I would move the tension to the... You know what? I would argue that tension ends up being, correct me if I'm wrong, mg divided by cosine. 650 divided by cosine of 8 degrees. Over here? Well, yeah, I want it to be 1 fraction equals 1 fraction so that stuff can move diagonally. Mac, normally I don't bother writing that, but since tension's on the bottom, I just wanted to reinforce, oh, you know what? We can swap those two. Really what we're saying is you would times tension to the other side, and then you would also at the same time divide by cosine, right? Is that okay? You get 81.3 newtons? Sorry? Oh, I didn't do the 8. Jeez. Let's try that again. That looks way better. 656 newtons. By the way, what if he was dangling straight down? What would theta be? 0. What would the tension be? Exactly mg. So if I hear you correctly, if I went 650 divided by the cosine of 0, oh, I do get 650 back. That confirms, I think my system here is right. I'm good with this. Okay. What did C want us to find? By the way, part A said write an equation for the forces. There would be my first equation if they really wanted me just to write the equation. You may notice I'm skipping over the write the equation section of a lot of your homework and just say, oh, go solve it. You'll write the equation along the way. What does part C want me to find? Normal force. Oh, which trig function could I use to find the normal force? I think I'd go tangent. But I could go sine and use tension. The only risk is if I've got tension wrong, I'm getting this one wrong. So I'll use the one that they gave me. I'll use tangent. Tangent. No, I went with blue, Mr. Duke. Of theta equals opposite over adjacent. Here to get the normal force, I'll just times by mg. It's going to be 650 tan 8 degrees. You get 91.4. By the way, let's do our test again. If he was hanging and theta was 0 degrees, if he was just dangling there, what would the normal force be? 0. Let's just double check, because I'd like to know, is my system right? If I put a 0 there, you're telling me I should get a normal force of... Okay, this is confirming kind of... I gave you guys the strategy of testing the extremes if you're not sure if your system is correct. I'm going to bring back because I want to use my answer button. I want that number stored. Why do I want my answer button with the 91.35? What does part D want me to find? Friction. Friction is what times what? Oh. I don't know. Wait a minute. I do know the normal force. I don't have to go look. Did they tell me what's mu? I think they did in the diagram. Did they not? What is mu? Why is it so hot? He's wearing rock climbing shoes. Oh, yeah. If you're wondering, that's part of what you're doing when you wear special equipment when you're rock climbing. You definitely want a nice big coefficient of friction. It's also what the chalk helps to do as well. Removes any moisture from your hands, which would lower the coefficient of friction. So it's going to be 0.65 times 91.4. I'm going to use my answer button. 59.4 newtons of friction force pointing up, and that's because right here he's pushing down with 59.4 newtons of force to keep himself from rotating, from spinning. That's what's helping him prevent spinning. So I know it's kind of weird, friction didn't appear in our free body diagram. I'm arguing it's a secondary effect. It's actually not preventing him from falling, it's preventing him from spinning in place. Is that all right? Again, let me emphasize here, I'm planting the seed. Cool, but not on test. Skip 6. Want to show you just what we can handle with our skill already. So here we have a cone, and inside the cone we've dropped a 5-kilogram ball. And this is asking, find the normal force that the frictionless, I have to make the walls frictionless, otherwise this question gets pretty yucky. Find the normal force that the frictionless walls exert on the 5.0 kilogram ball. Okay. Well, could we handle this? First thing I'm going to argue is we can split this dead in half. I'm actually going to solve for half of a ball. Each normal force is taking half of mg. And I'm going to draw a free body diagram on just half of a ball. I'll do the left half right there. What are the forces acting on that ball? Get the obvious one. And I'm going to go like this, mg over 2, because I'm arguing that only the left normal force is taking half of gravity, the right normal force is taking half of gravity. What else? Look at the picture. I think there's a normal force that goes this way. Now, that's it. Wait a minute, Mr. Dewick. That can't be at rest, because if I add those two together, tip to tail, I don't end up back where I started from. Well, here's what's happening. Let's take this normal force, and let's break it into components. It's got one component going straight up, and it's got one component going straight sideways. Where I'm pretty sure, I got to get my angle right. It looks like next to a vertical line. Oh boy, I got to draw this properly here, Mr. Dewick. I'm going like this, like this. So that's 22 degrees. That makes this 90 degrees right there. So 22 degrees right here, Mr. Dewick. Let's get this drawing correct. That's 22 degrees, that's 22 degrees, that's 22 degrees. Okay, had to think about it for a second there. This part here, I'm going to call fx. This part here, I'm going to call fy. Over on the right-hand side, I would actually end up drawing the same free body diagram. I would have mg over 2. I would have normal force going this way. I would break it up into Fy and Fx with an angle of 22 degrees. And Colin, my argument is these two here, they cancel each other. Part of what the normal force is doing is pushing sideways against itself from either wall. And if you don't believe me, can you use your imagination? If one of these walls vanished, say if the right-hand wall magically vanished, the ball would accelerate, fall that way. Okay? What I'm really going to say here is, hey, mg over 2 is being canceled out by Fy. Fy, which trig function? Opposite. Oh, really? Is it Fy a sine again? Well, that'd be nice. So we really have this. Mg over 2 equals, what did we say? I think it's going to be normal force times the sine of 22. This question said find the normal force. How would I get the normal force by itself? Okay. Again, Lewis, this is tougher than I'd ever ask you on a test, but for what it's worth, we got the tools to handle it. We have to scratch our brain a little bit and really concentrate and kind of do some visualization here. What was the mass? I've scrolled down. Let's write my numbers. 5 times 9.8 divided by 2 sine 22. By the way, I've skipped this question every single year I've taught Physics 12. You're the first group I've done this one with. I figured you guys could actually follow the argument, and I think you are, so congratulations. This is harder than I ever go. And I get a normal force of 65.4 newtons. Sorry, pause. We're going to finish off with a short little video that asks, what happens if an unstoppable force meets an immovable object? You've heard the phrase. We can define that in terms of physics. But first, what's your homework? Absolutely number one. I'm going to give you lots of lawnmower questions. So number 1 and number 2 are great. Notice in number 1, your diagram, you're pushing down. Number 2, in your diagram, you're pulling up, which means I think in number 2, your normal force is smaller. In number 1, your normal force is bigger. So just be very cautious of that. I would do a good free body diagram. 3 is cool, but I'm going to pass. By the way, 3 pushing straight down, all that happens is your normal force now is going to be mg perpendicular plus 12 newtons. For what it's worth. But I'll pass on that one. Here we go. Number 11. Number 12. 13. 14. 15. These are all lawnmower questions. 16.